So we're almost done with our discussion of Project Reactor and fluxes. We're just going to take a look at one more case study, which will illustrate some interesting things. It's going to show how you can integrate Java streams operations like generate, limit, map, and collect with Project Reactor Mono operators. And this is kind of a neat example of how you can merge together two different paradigms into the same program. And we're also going to show how to implement a Java streams collector that works for asynchronous mono objects, which is actually quite cool. And we'll see how that works here in a second. So this occurs in the ex6 project in the reactive Flux folder in my live lessons GitHub repository. So here is the ex6 project. You can see that there are several different methods under test here. There's one called test fraction multiplication streams. Then there's another variant of that. And then there's actually two variants of those, which show off different features of combining things in different ways. And as usual, we run the async task barrier to wait for all the tasks to finish. So here is this program. We create a random number generator. The first example here is going to call this helper method called getMonoStream. So we're going to get a stream of random mono to big fraction objects that are being reduced and multiplied concurrently. So let's take a look at that method. So this is kind of funky, so check this out. So getMonoStream is going to use Java streams operations. So this is not Project Reactor at the moment, it's Java streams. So we're going to use the generate factor method to make a bunch of big fractions. We've looked at make big fraction many times. It just makes a big random fraction that's not reduced. We're then going to use the streams limit operation to limit ourselves to this constant. And then we're going to use the streams map operation to reduce and multiply all these fractions asynchronously. Now notice a couple things here. This is really funky. So first of all, if we take a look at reduce and multiply fractions, you'll see that reduce and multiply fraction returns a mono to a big fraction. So this is all Project Reactor stuff using monos. So we're going to reduce the unreduced fraction in the background on the provided scheduler, and then we're going to go ahead and multiply the reduced fraction by a big constant. So this is going to return a mono to a big fraction. However, this is being used in the context of Java streams. So we're going to end up with a Java stream of monos to big fraction objects that are being reduced and multiplied in the Java common fork join pool. So here we're using a special adapter scheduler that will take this particular executor, which is a Java streams executor, this is the common fork join pool, and then use it in the context of doing computations using Project Reactor. So that's a little bit uncharacteristic, but it's cool. So we end up with a stream of monos to big fractions. So then we take that stream of monos to big fractions, and we're going to collect them. Keep in mind that what we're doing here is we have a Java stream of monos to big fractions, and we're calling the Java streams collect method, and we're going to create a mono list collector, or monos list collector. So two mono list makes a new monos list collector. Here is monos list collector. It's a Java streams collector that takes a stream of monos to items of type t, in this case big fractions. It stores them in a list of monos, and it returns a mono to a list of type t, in this case big fractions. So we're totally merging paradigms. This is Java streams collector used to collect monos, and it's really quite fascinating to see how this works. So here's the supplier. It returns a new array list to store this is the collector accumulator that accumulates the results. Here's how we add the next item. We use list add. That's really pretty similar. We can use the combiner. Were we to use a parallel stream, which we're not in this case, which would add one collection to the other. And then finally, here's the real important method. This is the finisher method. And this took me quite a while to figure out how to write. So what we do is we've got a list of monos, and we take that list of monos and we use the when method. So the mono class has a method called when, which is somewhat akin to the completable futures all of method. And what this does is it takes a list of monos, and it'll return a single mono that will complete when all the monos in this list complete. So those things will all be running in the background. When they all finish their asynchronous processing, that mono will emit. And then we use a very funky sort of Eastern philosophy, Buddhist kind of thing of materializing the results. So it's going to return a mono that signals when all the monos complete. And then at that point, we're going to take the original list of monos, turn it into a flux, use the block method here. And what's interesting about this is that, let's see, we can do that. So this is going to basically convert the monos to items of type T into items of type T. So now we have a flux of items of type T. This call actually will not block because we wouldn't have gotten here had everything not finished running when we materialized it. And then we collect the results into a list of type T. And we could probably replace that with just toList. Oops, maybe not. Oh, no, we can't do that because it's a flux. Sorry. So in this case, we're going to collect the results to a list, and we end up getting back a mono to a list of items of type T. So that is what that particular method does. And then we're going to sort and print the list. And I think this is the typical technique we use where we do the sorting in parallel, and then we apply the first with signal method, which will take either one of those things that finishes first, and that's what we will end up printing. The result of the sort that finishes first will go. So that's that method. This is showing how you can combine Java streams with Project Reactor in a very interesting way. We have a couple of other examples here where we're just showing other features. So in this particular case, we're going to create that mono stream, collect them into a mono list, and then we're going to use something called flatMapIterable. And flatMapIterable is going to convert the mono to a list of big fractions into a flux of big fractions. So now we have a flux of big fractions by using flatMapIterable, which converts, as you can see here, a mono to a list of something to a flux of those things. Then we sort and print that. And then the last version that we have here does something very similar, where we're going to have another collector called the toMonoFlux. So before we had a collector that we called toMonoList. It was the monos list collector. And then down here, we're going to have yet another collector, which is the monos flux collector. And what this is going to do, it pretty much everything is the same as we had before, except this is going to return a flux of T instead of a mono to a list of these things. And so everything looks pretty much the same, except down here, before we used flatMap, and now we're going to use flatMapMany. And so flatMapMany is going to take something that's a mono to a list of stuff, and it's going to turn it into a flux. So it's just kind of short-circuiting things a little bit. So if we look at mono's list collector, you can see what we did is we took this and we collected it into a mono to a list. Whereas in this case, because we want the thing back as a flux anyway, we're going to short-circuit that conversion into a list and just convert the mono into a flux, which is ever so much cleaner. So those are all the different variations we have here. Just for kicks, let's go ahead and run the program and see what the results are. And it's just going to go ahead and do those operations with creating random big fractions and then sorting them and reducing them and sorting them and so on. And these are just printing out the results. You can see that they're provided in sorted order. So that's the final case study for Project Reactor and Fluxes.